All right. Well, firstly, thank you so much for inviting me here. It's been really wonderful to be able to listen and learn from so many people who have had experience with APL. As a relative newcomer to APL, I have to admit I don't know many people at all. Well, I don't know many people at all who know APL as a language itself, and very most certainly don't know people who know APL in as much depth as the people here. So, as is, I think, tradition for this competition, I will be talking a bit about my experiences with APL during the competition. But before I do that, just like to thank Dyalog again for this wonderful opportunity, as well as the competition sponsors, Fiserv and SimCorp, and also to the competition organizers and writers that Brian talked about, because this competition was extremely fun, and I really appreciated all of the work that went into it. So what I will talk about today is briefly a bit about my background, and then I'll talk about just a few of the problems, and then some reflections on what the good things were, and some thoughts about what I might use APL in the future for. So I'm an undergraduate student at Monash University in Australia, a long, long way away from everywhere else in the world. But we are somehow part of the Eurovision Song Contest, so I suppose we are part of Europe. And this is a photo of one of the buildings in my university. At Monash University, I study medicine, which is, for our particular course, a degree you enter straight out of high school. It's a 5 or 6 year degree. I've just finished my 4th year last year, and I'm doing the optional research year this year, and will graduate at the end of next year. But despite my main area of study being medicine, I have a strong interest in programming, and I started to learn how to program roughly just a little bit after I started medical school, and mostly because I was looking for ways to solve problems in ways that I could give instructions to a computer. There are a lot of problems in medicine, and some of the ways that we deal with these problems I feel are getting a bit old. So the ways that we do, for example, algorithms in medicine, or how we incorporate evidence-based medicine into our practice, it's as though we're trying to execute the instructions that oftentimes would be much better relegated to a computer. I started off with learning Python as my first language, and very, very poorly written Haskell. But over the years, I've had the wonderful opportunity at my university to work with some great professors on some summer vacation research projects using a number of languages, including MATLAB, R, Fortran, modern Fortran, and JavaScript. But what I normally use programming for nowadays is predominantly with Python or Elm. Python, of course, being a general-purpose scripting language, which I usually use for a number of automation tasks and for writing some back-end server code, and Elm as a pure functional language, very similar to Haskell, but without type classes and some of its capabilities of abstraction. And I use Elm for front-end client-side web development. My preferences in terms of language, programming languages, are for a statically typed functional language, very similar to Elm or Haskell. And in terms of my preference for an editor, I am on the Emacs side of the fence. But I do, I do like Vim key binding, so I use the evil Vim emulation in Emacs. And it's actually a very nice environment. You sort of get the operating system nature of Emacs as well as the text editor nature of Vim. And in terms of how I came to know about APL and the APL family of languages, so I kind of got into this through the wide world of the internet. When I was learning to program, one of the things that was recommended on a lot of forums was to learn through solving problems. And one of the problem sites that was recommended was Project Euler, which is a repository of a lot of mathematical problems that you can solve in a variety of different programming languages. And when you solve a problem, you get access to the forums. And I always remember I would spend so much effort trying to solve a problem with Python, and it would often be maybe 10 to 20, 30 lines of code. And when I looked at the forums after solving it, there would always be this one-liner J, K, or APL solution, which just blew my mind because I felt so proud of spending so much effort writing all of this code, and you could just write it in a single line. So that I didn't understand anything about APL back then. But part of how I came into getting interested in learning APL was through news aggregators. And as much as I hate to admit it, I have to admit, I think a lot of my thinking is influenced by what I read online. And a lot of these sites, particularly Hacker News, there's a lot of I think there's a lot of interest around APL family languages. And I remember very distinctly seeing the Codefund's live stream where there was a lot of discussion generated about what it meant to write code, because all of the conventions that I guess people learn when they're learning programming were sort of defied in this code base. And one thing I also distinctly remember is the kind of mythology surrounding Kay and Arthur Whitney and his ability to fly in the face of all normal conventions. And I thought this was very interesting stuff, but I didn't really have much reason to use APL until I sort of came upon the competition and Dyalog itself. And how I came upon Dyalog was through John Scholl's Game of Life video, which is this really amazing demonstration of what APL can do in very limited space, and how well it can express these array-oriented ideas. And of course, if you look at that Game of Life video, you'll come into Dyalog defunds and the website and the company Dyalog itself. So that's pretty much how I came into the competition and how I learned about Dyalog. When I was doing the competition, I was using the RIDE development environment on Fedora Linux, and I've found it quite interesting to use. I have to admit, it's quite different to how I usually program, but it was very helpful to have those tooltips to learn when you hover over the primitives, and that's basically how I learned APL, by hovering over the primitives and looking at the examples. I did find the Mastering Dyalog APL book to be quite helpful. I think I only read the function definition part to learn about the tacit and the defunds operators, the defunds and the tradfunds ways of defining functions. The rest of it I wasn't able to get time to read, but it was a very great reference point. You probably can't see this, and I apologize that it's so dark. This is essentially what I submitted for the competition. I don't show you this so you can read it. The reason I'm showing you this is because this is all one file just split over multiple screens. I wonder if I can, will that work? No, okay. Well, that's all right. Essentially, I very aggressively commented my code because it helped me understand what I was doing. And you can see, for example, in this, well, maybe you can see, but all the gray stuff is code, and there's only actual 5 lines of code in this particular panel, whereas the rest is entirely comments and diagrams. This was kind of to help me understand what I was doing when I was problem solving through this competition. I guess in a real code base, I probably wouldn't be so tempted to write so many comments because, of course, you're manipulating the code while you're running it. But through this particular submission, I felt like it would be very helpful to explain what I was doing. And also, I put this here because even though I've got no comments on the rest of the slides, I did comment what my code was doing. And one thing I did comment, so you can't see it, but one thing I commented for most of the functions was types. And that's because one of the things I really do when I program nowadays is think about types and the type transformations. So that's probably the main source of most of the comments. So I'm just going to go through quickly some of the problems. This is the very first problem of the easy set, and the problem is to define a function grill, which takes a left argument grill and a right argument character grid, and returns the hidden message corresponding to positions of spaces in the grill. So it's basically putting this character matrix and superimposing it over this second character matrix, and wherever the spaces are, saying where the letters are and putting that together into a single character vector. And you get a message out. So you'll see in the next few slides that I've got kind of diagrams explaining what the process is, as well as the actual code I submitted. Again, there are many ways to solve most of these problems. This is just the way I chose to do. So what I did was flatten both the grill and the grid using the enlist primitive, and create a Boolean vector corresponding to the spaces, and use that to Boolean mask over the grid to form the message. And that's basically it. I think, yeah, the first few problems were quite simple. The next problem, this was the third problem of the first easy problem set is to define two functions, tap encode and tap decode, which converts between a message and a tap encoding as defined by a Polybius square. So essentially, if I give the character vector APL to this function, first you find where the A is in this grid, which is in the 1 and then 1 coordinate, and then you find where the P is. So the P is in 3, 5. So you have 3 taps and then 5 taps, and then the L is in 3, 1. 3 taps and then 1 tap. And then you're supposed to write a function tap decode which goes the opposite way. So the way I wanted to approach this problem was because I'd found on the Dyalog dfunds website that you could write invertible functions, and this seems like absolute magic to me, that you could write a function and have it automatically be invertible if you write it tacitly. I don't know if this is used in real production code bases, because I imagine that there are some limitations to what you can understand when things are not quite as transparent and when they're done automatically for you. But I really felt like this problem was a great one to try get some invertible function that would do tap encode and tap decode the opposite way. Almost achieved that. I couldn't find a way to get... Oh, I'll just explain this part first. So basically the way I chose to solve this problem was to get a message, convert it into alphabet indices, which would then be converted into coordinates for this Polybius square, and then render, so this, after this step, you get something like 1, 1, 3, 5, 3, 1, and then you simply need to render that to get the actual string. And then going the opposite way, you just do the exact same thing, but in reverse. So you parse this into 1, 1, 3, 5, 3, 1, and then you apply these other functions to convert the Polybius coordinate back into the message. And you can do that with an invertible function for locating it in the alphabet and for putting it into the Polybius coordinates. So to make this invertible, I had to jump through quite a few hoops because this particular problem is not symmetrical. So when you have an input that has a J in it, the I and the J both map to the same tap encoding. But when you go the other way, to go from this back to a character vector, if you get something that's this ambiguous 2, 4 taps, you're always supposed to convert it to an I. So if you try to do this naively, you'll get a domain error when you try to do the inversion because you can't invert something which has 2 possible outputs. Well, that's what I thought. But apparently, I think this is a bit of an abuse of what the inversion does, but I tried my best to find a way to get the I and the J to map to the same encoding, but when you go the inversion way, you don't get the J. So I had to define a new alphabet and put the J at the very end, and then do a bit of manipulation on the indices to actually make sure that the J would map to the same thing as the I, but you're not touching any of the other letters encoding. So that way, when you go the inversion way, and you have something that could map to either I or J, it will always map to the I, not the J. And then it was very fun to try and work that out. And then all you have to do for the actual stringing the functions together is to do the rendering of the tap knocks of the locate. And then when you go the other direction, you basically invert this composed function and just put that after the parsing step. So I really wanted to find a way to get that parsing and the rendering to be invertible, so you could just write tap decode as the tap encode obverse, but could not find one. If you are able to find one, let me know, because I'm very interested. Okay, so this next question was another easy problem. This one asks you to define 2 functions, make mines, which takes a left argument, number of mines, and a right argument, board size. So for example, if you say 11 make mines 5, 8, it's asking you to create a board of 11 mines in a 5 by 8 matrix. And the mines are represented by these neg1s. And then you're also supposed to define a function, count mines, which replaces those zeros with the number of mines that's surrounded in a 3 by 3 neighborhood. And this is basically Minesweeper. So the way that I approached this problem was to, most of the time I usually just wrote these in the interpreter, but when I came back to write this presentation, I found it a bit hard to read what I'd written. So I tried to rephrase it in these diagrams to show the flow of information. The shape, I first take the shape and create a zeros vector with the number of elements equal to the number of elements in the given shape. And I also use that to create to deal the number of mines in to create a vector of indices into this vector, which you then use to place neg1s into the zeros. And then the final step is to simply convert that neg1 0 vector back into a matrix using the shape to the original reshape. To do count mines, this problem I thought was nice to try and use a fork. I quite like tacit programming, and most of my solutions I tried to find a tacit way to do it. So the first time, you basically use the stencil operator to find the 3x3 neighborhood of each cell and sum the absolute values. So for example, in this particular cell, the 3x3 neighborhood includes only this -1, and they're taking the absolute value of that would give you 1. And then you sum all of those in the neighborhood, and then you use a a Boolean matrix corresponding to the positions of zeros in this matrix to then produce a mask over that original stencil. And the reason we do this is because we don't want these neg1s to change, so we keep the neg1s as neg1s. And because 0 times anything is 0, you have to take away 1 at the end to get those zeros back to neg1s, and because you take away 1, you have to add the 1 back into the stencil operator. So that's what these functions are doing. I always find APL a little hard to read when I come back to it after a while, but I think it's really nice that I think in Dyalog APL and I think in J as well, you can write a function and have it represented in a tree format to understand the flow of the functions. So this is one of the medium problems, and essentially you don't have to read all of this. Basically, you're just implementing this mathematical function to write an operator that will estimate the integral of a function by finding points and creating trapezoids with those points, and then finding the area under a curve with that estimation. I think it was very generous. They basically just gave you the formula, and you could just implement it directly. The way that I approach this problem, and I always like approaching these problems by splitting them up into smaller problems, was to basically just make sure I could get these particular numbers, so delta x, or the width of every trapezoid, the actual numbers in a subinterval themselves, so from x0 to xn, given some argument telling you how many intervals you want to split it into, and also the range you want to split that interval into, and also a function to create the coefficients, which are 1, 2, 2, 2, 2, 2, until the last one, which is 1. So once you've got all of that, all you need to do is really just translate this directly into a function in APL. So you find the delta x over 2 times the summation of the function applied to every point in the interval times each of the coefficients element-wise. And I thought this was really neat that you could do this in APL because it looks, well, maybe if you're not familiar with APL, it doesn't look very similar, but if you this I can understand without having too much trouble. This is basically what this function does. I just wrote it in a way such that all of the previous functions are pure functions, and you chain them together at the end, which is why the alpha and the omega appear in this function multiple times. I prefer this style of programming coming from an Elm and Haskell background where you're only manipulating pure functions. In terms of the actual implementation, I think most of the time I kind of get this schematic of how the problem's laid out in my head first, or write it down, and then I just try to, because I know what each part of this is doing, try to work in the interpreter to come up with how exactly to implement that. Yeah. So this second medium problem is to implement Romberg's method. And I'm not a mathematician, so I don't know if this, so this particular problem asks you to implement a recursion relation that uses the trapezoid in the prior problem. But there is a certain desire for you to not calculate f more than once in each point, and for r, m, n only to be calculated at most once for each m and n. Now, I don't know, maybe if you're familiar with mathematics, this sort of, the structure of how to do that would be easy to understand, but for me, I could not do this without writing this down on paper a few times and then getting this very clear in my head what exactly was depending on what in the recursion relation. And eventually I was able to find some sort of tree-like structure which basically says that this r for this particular m value, for this particular n value, depends on this prior value and this prior value. And when this is clear, I think it's much easier to find a way to do to only traverse this once. So the way that I did this was to do a recursion, two recursions. So the first recursion goes up along this diagonal, and the second recursion goes down the columns. So you end up calculating these values in the order 0, 0, then 0, 1, 1, 1, then 0, 2, 1, 2, 2, 2, then 0, 3, 1, 3, 2, 3, 3, 3. And at the end, the final value is your actual answer. And in each intermediate step, you keep the values in the previous column because that's the only thing that's depended on. And you gradually build this up. So I don't actually know if this is particularly efficient. And I didn't really try to address this first part because that would require rewriting the trapezoid function, and I was just lazy. I felt like this was really nice because I would not be able to do this in another language, even in Elm or Haskell, where recursion is kind of king. The ability, the fact that APL is so succinct meant that I had no uncomfortable feelings about writing this out on paper multiple times and rewriting this a lot, because I knew that writing it out at the end would be so cheap. I could just write it out in a few characters. And in Elm or Haskell, I think I'd be very tempted to model this directly in the program, and I'd probably end up with some very flimsy abstraction that's not entirely good. So that's kind of how this one turned out. So finally, the last problem set, which I'll talk about, is the cube problem, which is the difficult problem I tried. I tried most of the problems, so I did 3 of the easy problem sets, 2 of the medium ones, and 1 of the difficult ones. And I really liked this problem because I felt like it was a good demonstration of the power of APL. So this particular problem asks you to model a pocket cube, a 2 by 2 by 2 Rubik's Cube, in an internal representation of your choosing, and they were very vague with what this was, so you could basically choose anything, and you would either make life very difficult for yourself, because the next steps of the puzzle would be difficult, or you can make life very easy for yourself if you chose a good representation. But it's hard to think about what that representation would be initially, and at least after numerous times doing this problem, so I rewrote my solution to this a fair few times. I eventually tried to represent this Rubik's pocket cube as a 2 by 2 by 2 array, which makes sense because a pocket cube is a 2 by 2 by 2 cube, and then putting in each of those cells a 3 by 3 matrix of zeros and ones, which indicate unit vectors that are all orthogonal to one another. And by doing this, you can know definitively the orientation of each cube in the whole pocket cube using these 3 orthogonal vectors, the axes of which I chose to represent the APL axes, so x is down, y is that way, and z is that way. And once you have that representation, you're asked to write a function that unfolds that cube and creates a net in a character matrix. The way that, maybe this is a bit small, but the way that I chose to do this problem, because I wanted to make life easy for myself for the next problem, which was to twist the cube, was to put all of the information into this matrix. So there's no information here about what the sides actually are or what the colors are. All of that's in the unfold function, which basically takes the cube and extracts the 6 faces, and then it finds which unit vector is pointing outwards for a particular face. So if I have this face, and I know that the orientation has been changed so that a different unit vector is now pointing in that direction, and because all of these mini cubes have the same colors as each other, it's just that some of those sides are hidden, you can know definitively what unit, if you know what unit vector is pointing outwards at each face, you know what color it has to be. And the actual implementation of this I'm not very happy about, but essentially you basically take a character matrix of each of the characters representing colors, and you index into that character matrix using a special function which I wrote, or a special operator which I wrote, which takes some parameters and gives you what face and what unit vectors you care about. So I think this is a bit hard to explain on a presentation slide. It's really something that I had to work in the interpreter for. But essentially, the high-level overview is you take whatever unit vector is pointing out for each side, and you check what orientation it is. Then you match each unit vector to the corresponding color, which will give you the actual faces. And then all you have to do is to pick those faces out. So pick whichever face you're interested in for the net and assemble it into that character matrix. And you have to do a bit of rotations and transpositions to make sure that the net unfolds in a correct way. But that's basically how the unfold function works on this pretty bare data structure. So the final problem I'm going to talk about is the second part of this question, which is twisting the cube. So twisting the cube, they've put a special notation to say that if you get an F as your character, you'll rotate the front face clockwise. If you get a B, the back face clockwise, and so on. And there are a few whole cube rotations where you just rotate the whole cube. So the idea for this problem was to write a function twist that would take a right argument cube and a left argument character vector indicating a sequence of rotations. And you can add a prime or two kind of primes or quotation marks to make that rotation counterclockwise. So in effect, you have 18 different transformations to twist this cube. The idea behind this particular data structure I chose was so that this would be easy for me, because I felt that this rotating the cube sounded like a good problem to just apply rotation matrices and do a matrix product. And these are basically just very standard rotation matrices you can find in any textbook, except that I had to reverse a few of them because this particular axis definition doesn't follow the right-hand rule. I chose to preference the APL axis in preference over it. But essentially what you do to apply these transformations is you need to rotate each of the matrices, the unit vector matrices, inside each cell, and then you need to shift the positions of each of those cells in the actual cube. So if I twist the top layer clockwise, you're rotating the cubes themselves, and you're also changing the positions of the cubes in the big pocket cube. So that's what this the U shift and the U rotate functions are doing. They're doing the U rotation shift and the U rotation rotation, and then you simply compose them together to create the actual transformation. And then you do the same thing for the whole cube transformations. So all of these functions, U, Singmeister X, Singmeister Y, and Singmeister Z, take a cube and return a new cube. That's basically the transformed cube after applying the rotation. Then once you have all of those 18, well, you can specify every rotation in terms of these 4 rotations, the U, Singmeister X, and Singmeister Y, and Singmeister Z. For example, the front rotation, you can basically just put the front on the top, do the top rotation, and then go back to put it back where it was. So you're always holding the cube in a known orientation. And I struggled a lot with thinking about how exactly to map characters to functions. And I was hoping that APL you would be able to box first-class functions and index into an array of functions, but I don't think you can do that. So what I ended up doing was doing a guarded defun to map, which I'm not really satisfied about, but I couldn't think of another way to do this, but which this essentially maps all of those different Singmeister notation characters into combinations of these 4 rotations, which is clearly not the most efficient way, but it's very easy for me to do, and it fits on a single slide. And if you want to do an anti-clockwise rotation, there's a special Boolean which indicates that. So now you have a way to map a character and a Boolean indicating whether it's clockwise or counterclockwise to a rotation and a shift function, which takes a cube and returns a new cube. So now the only thing you have to do after this is to take the cube as the first element and fold all of the instructions to the left of it. So you apply the Y rotation to the cube with a non-clockwise rotation, an F rotation, and so on, and that way you apply all the rotations in sequence. And the final step is to make sure that you can actually get that character vector and return it into this kind of separated characters with possibly a counterclockwise rotation. So a vector containing pairs of a character and a Boolean indicating whether it's supposed to be clockwise or anti-clockwise, and then after that you just fold left. And that's basically that twisting function. So those are the problems I wanted to talk about. As you saw on the previous slide, or maybe it was too dark, there were a lot of problems. And I'm not satisfied with my solutions for all of them, because I think after coming here I realized so many different ways in which they could be solved, which would be ways that I think would have been better than what I submitted. But I wanted to very briefly talk about, do I have time? Okay, very briefly talk about my experiences, the good things about APL and my reflections on things that I might use APL in the future for. So the biggest thing for me when doing this competition was just how productive it was. I think this was the most productive I've ever felt with a programming language, despite all of my experience using Python and Elm, which are really nice languages. But I kind of had this experience where after this competition, for 3 days, I actually could not bring myself to program in any other language because I knew that there was a way to do this in a few characters in APL, and writing it out in Python, like even list comprehensions, which are a terse way of defining map functions in Python, or to do basically do a map in Python, is really terse way of doing things in Python, but even that felt utterly verbose compared to what you could do with APL. And this was probably bad. I hope my supervisor is not watching this, because I do Python as part of my research project, but I kind of just came to a standing halt with my research project for a few days because I couldn't program in Python when I'd been poisoned by the APL way of doing things. The other thing I really enjoyed about this competition was the ability to do paper programming, or paper problem solving is probably a better way. And because I have a few photos of what I wrote during this competition. So these are actually things I did on my notebook during the competition, which is why it's so untidy. But you can kind of see that I messed around a lot with trying to figure out the relations for that particular Romberg's problem, and eventually, after a few tries, came along the actual tree kind of dependency. And for this cube problem, I really loved this one because I spent so much time thinking about it and rewrote it a few times. But it really helped me think in more dimensions than 2. I'm still not good at thinking in more dimensions than 3. I find it very hard to think about 4-dimensional structures. And actually, I was wondering, maybe you can represent this as a 2 by 2 by 2 by 3 by 3 5-dimensional matrix. But I found that really hard to wrap my head around. But this problem I spent a lot of time thinking, and some of it actually made it into my code. So this particular part is actual APL code that I was able to write on paper, which I don't think I can say about any other programming language I've done. But I think when the programming language is verbose, I feel like there's an investment you have to make in writing it out the first time, because I feel like it's too costly to write it out multiple times that I end up trying to do it all at once in the first time. So that's the other point about disposability. I rewrote most of my solutions multiple times. The first time I wrote a solution was to understand the problem, and the second time was to actually write a solution. Because I think when you come to these problems the very first time, you just don't understand the best abstraction, or in any case, a good abstraction, until you actually get in there down and dirty and manipulating things. And then once you've actually written a naive solution, you can think about how to make it better. And this is really easy to an APL as opposed to things like Python or Elm, where it's much more verbose and you kind of feel committed to the code you write. Expressiveness, I really liked composability. I found it even easier than writing composable functions in Haskell and Elm, because all functions in APL are limited to only 2 arguments. And I found that a big difficulty at first, but I actually find that this makes composability much easier because it's so much simpler to write combinators and in tacit programming when you only limit yourself to 2 argument functions. Great primitives make expressiveness easy. Symbolic expressiveness, I actually tried writing J using an add-on which converts the J primitives into English words. And I tried to write k-means clustering in J using the English words, and I was hoping it would look like English. But there was an error somewhere where I wrote it, and I couldn't find where that was with the English. So on my bus home, when I was, after I'd done that somewhere in the library, I was working on J on my phone, because J has an Android app. And I found that I wrote the k-means clustering again on my phone, and then when I got home, it just worked, as opposed to the English one, where I'd spent some time trying to figure out how to, manipulate the words into some combinator tacit programming. So I really think the symbolic point is super, super important. I probably didn't realize this until after I had that experience where writing the English was harder than writing the J characters on my phone. I think Iverson's notation as a tool for thought didn't really hit me until that moment. And maintainability, I think this is the one thing that a lot of people, when they come to APL, are a bit, well, at least I know I was a little bit unsure about, but the kind of REPL-driven nature and the transparency of idioms over libraries was, I think, really makes it easy to maintain APL. I don't know in comparison to other languages whether it's easier, but it's not as hard as it seemed to me at first. So in terms of my thoughts, the competition was absolutely awesome. I really loved it, and I think it's really underappreciated. I feel like you guys should get so many more participants, because it's so obvious how much work goes into making this competition run and how much work went into writing the problems. And they're really good problems. And I really hope more people participate in the future. APL, I really like APL, and I want to use it in the future, but there's something that's holding me back. So I thought a lot about this because I absolutely love APL as a language, but the things that keep me coming back to Python and Elm for productivity's sake are things like tooling and libraries. And I think this is really important nowadays. For example, my research project this year uses TensorFlow, and there's absolutely no way I could write that in APL. I don't have the experience to write the underlying libraries for machine learning in APL, whereas having these libraries accessible to someone like me, who is not a programmer by trade, means that I can be productive even without knowing the internals of the machine learning library itself. Static analysis is also a big thing for me, and I find that, well, I know some people may see these as crutches to cope with a lack of competency, but I can say that without a doubt I am more productive because of static analysis tools. And even dynamic languages like Python can get static typing checks thanks to libraries provided by Dropbox and Facebook. And that's a really nice experience. And since I'm an Emacs user, there is a Dyalog Emacs mode, but I haven't managed to get it to work with the REPL. But yes, the Emacs integrations for a lot of the languages I use are really nice, and I really crave something like that for APL. The wider community, I think, so most of my learning was done in the interpreter, and there are so many things I didn't know you could do until after I came here to this conference. I didn't know you could do regex replacements, and because I guess that's a quad function, it's not one of the primitives that I usually learn, but that would have helped me for some of the problems in there a lot. It would have been much more efficient. Adoption is always something that's, I think, a big player. The reason I think a lot of things like Python and Elm have great tooling where you can get basically things like type-based searches or code generation based on type signatures is because of the adoption around these languages. And that's something that I'm still struggling with APL, because the tooling with APL sounds like it's getting so much better from what I've heard at this conference so far. But I'm always a little cautious trying to learn something which is I guess with a niche community. I remember I tried to convince one of my friends to learn APL and to enter this competition, and I showed him APL, and the first thing he said to me was, "No one's going to employ you if you write code like this," which made me a bit sad inside. But I get his point. Like he comes from a master's of software engineering with JavaScript and Java, where you're basically writing a lot of code that's verbose but well understood by everyone. And I guess with high adoption comes this idea that you're getting something that will make you desirable. I think I and a lot of people in my position in my university who are also medical students who code, we are very lucky in that our livelihood does not depend on our ability to write programs. So we're happy to learn things that maybe are niche and will maybe not be the basis of our jobs in the future. But I can understand for a Masters of Software Engineering where their livelihood does depend on their ability to write code, that maybe this is not quite as desirable. The final thing, so I think it's absolutely wonderful, Dyalog's response to the open source community, and I think the non-commercial license without needing to put in your details is going to be huge, really great for adoption. I think there are always going to be people who find complaints. I mean, even with open source languages, there are always people who are complaining about the direction of the language and the inability to kind of contribute and that kind of thing. So I don't know if there's any good solution to this, but I always think there were people who complain about the lack of open source nature of Dyalog APL. I know GNU APL is open source, but it lacks a lot of the niceties that Dyalog APL has. I think that's one of the things that's also kind of holding me back a little bit, but I think because for my Windows computer here, I have the unregistered copy rather than the educational license, because I use my educational license for the Linux machine I have at home. But being able to have access to the APL interpreter, even if you're just using it for personal projects, would be really nice. And I think it's a wonderful thing that Dyalog's doing, and something I was so pleased to hear when I came to this conference. So, summary, APL is a powerful and fun problem-solving tool, and I really enjoyed it, and I hope I can use it in the future. Thank you.